All right, everyone, and welcome. Tonight, we're going to get stuck into something that's really at the core of what we do. That little bit of magic we call bouncing signals off the sky. It's how we chat with the world, and it's all thanks to that giant fusion reactor sitting 93 million miles away, our sun. So, you might be wondering, why are we talking about this right now? Well, it's because we've just come through the peak of solar cycle 25. And this cycle has been a bit of a surprise, giving us some, well, let's say, interesting conditions to work with. And this number, 161, it really tells the story. The official prediction, they were expecting a peak of about 115. But, well, the sun had other ideas, didn't it? It hit a smooth sunspot number of 161 back in October 2024. That's a much, much stronger cycle than we were told to expect, which has certainly made for some happy DXers. Right, so let's get back to basics for a moment. When you key your mic here in Grantham, where does that signal of yours actually go? Well, if you're chasing that long-distance contact, it's heading up, way, way up, on a journey to a part of our atmosphere we call the ionosphere. And this is where it all happens, the ionosphere. Think of it as this massive electrified region stretching from about 50 kilometers all the way up to over 650. Up here, the sun's radiation is so powerful it literally zaps the gas molecules and knocks electrons off them, creating this invisible, electrically charged mirror up in the sky. But here's the thing. It's not just one big flat mirror. The ionosphere is split into these distinct layers, and each one does a totally different job. You've got the D layer, which is a bit of a hurdle, the E layer, which can sometimes act as a trampoline for more local contacts, and then you have the F layers. The F2 layer. That's the Olympic-grade trampoline that sends our signals clear around the world. So how does this all work in practice? Well, the biggest thing that controls these layers, and by extension our propagation, is, you've guessed it, whether the sun is up or not. The daily rhythm of our planet completely changes the rulebook for HF radio. You really have to think of day and night as two completely different radio worlds. During the day, the sun powers up that D layer, which just gobbles up our lower frequency signals, while the F layer splits in two and opens up the higher bands. Then, at night, the whole thing flips. The D layer vanishes, the F layers merge into one, and suddenly the low bands, 80 and 40 meters, spring to life for those lovely long-distance contacts. And this SpongeBob analogy is just brilliant. The best way to picture what that D layer does during the day is to think of it as a great big, soaking wet sponge. Your signals on 80 and 40 meters, they go in, but they just don't come out. All that precious energy gets soaked up before it ever gets a chance to reach the higher layers to be reflected back down. But after the sun goes down, there's no solar radiation left to keep it going. That sponge effectively dries up and disappears. And that, my friends, is the moment we're all waiting for on the low bands. With that D layer out of the way, our signal suddenly has a clear shot all the way up to the F layer, ready to make that incredible bounce back to Earth, maybe thousands of miles away. Right. Just when you think you've got it all figured out, the daily rhythm, the bands, the sun can decide to throw a massive spanner in the works. Solar eruptions. These are the wild cards of propagation, and they can change everything in a flash. So, the first type of wild card is a solar flare. What is it? It's a colossal explosion on the sun's surface, a sudden, absolutely violent release of energy that shoots a blast of X-ray radiation straight at us at the speed of light. And because that radiation travels so fast, the effect is almost instant. It takes just 8 minutes from the flare erupting on the sun for those X-rays to slam into our atmosphere. They supercharge that D layer, turning it from a wet sponge into a solid brick wall. The result? A total radio blackout on the entire sunlit side of the Earth. Dead. The second type, which is often even more disruptive, is a coronal mass ejection, or a CME. Now, this isn't just a blast of radiation. No, this is a physical cloud of magnetized solar plasma. We're talking billions of tons of this stuff getting hurled out into space. And unlike a flare, this cloud takes its time. It usually takes about 1 to 3 days to get here. When it finally hits, it rattles the Earth's magnetic field, kicking off what we call a geomagnetic storm. And for us, that means really unstable conditions, signals fluttering all over the place, and sometimes total blackouts, especially if you're trying to work a path over the poles. So, the big question is, How on earth do we, sitting in our shacks, navigate this completely invisible, constantly changing, and sometimes pretty violent environment? Well, the good news is we don't have to guess. We've got tools. Now, a really key idea you need to get your head around is the maximum usable frequency, or MUF. For any path, let's say from here in Grantham to Australia, there's a ceiling. The MUF is the absolute highest frequency that will bounce back to Earth. If you transmit above it, poof, your signal just keeps on going, straight into deep space. And just look at the power we have at our fingertips today. It's incredible. These online tools are like having your own personal space weather forecast. You can pop over to the NOAA website for the raw data on solar flares. You can look at a live MUF map to see what the ceiling is right now in real time. And then you can use spotting networks like PSK Reporter to see where people are actually making contacts this very second. Honestly, a quick 5-minute check of these websites before you get on the air can be the difference between a logbook full of new countries and a really frustrating evening of calling CQ into a completely dead band. It's all about working smarter, not harder. So, to quickly wrap all that up, it really all starts with the sun. The sun creates our ionospheric mirror, its daily rotation tells us which bands are open and when, and its occasional temper tantrums can change the whole game in an instant. Getting your head around these basics is the real key to mastering HF. So look, we've built this entire picture of propagation around the sun's influence, and for very good reason, of course. But what if there was another force at play? Something else that could influence the ionosphere, and maybe help us predict conditions in a totally different way? It's a fascinating thought, isn't it? And it's one we'll be exploring next time.